Well, hello. Hey, we're at the chapter 8 review time frame. We've covered all the sections, and I just wanted to do a quick recap on what those sections were. So in section 8.1, we were working with net change, looking at integrals and their usefulness in particle motion, displacement, net distance traveled, that sort of thing. 8.2 brought us the area between curves. We could either do top minus bottom or right minus left. It was important to get the intersection points and then to determine whether we could do it in one integral. Sometimes it requires two if our top over bottom curve changes. 8.3 brought a lot of volume questions our way, and there were different techniques that we could use. One was cross-sectional area, where we talked about using semicircle, squares, rectangles, isosceles right triangles on legs, or isosceles right triangle on hypotenuse. Equilateral triangles was another one. 8.4, keep going on volume because there's more. Disk method, washer method, and shell method, all done perpendicular to a horizontal axis of rotation or else perpendicular to a vertical axis of rotation. If I'm perpendicular to a vertical axis of rotation, I'm working in Y's. 8.4 was the length of curves, fairly simple formula. It was the square root of, it's the integral of the square root of 1 plus f prime of x squared dx, or square root of 1 plus g of y, g prime of y squared dy. So you can work in x and y's with the length of the curve. And 8.5, normal distribution, just kind of a fun section to look at the area underneath the normal curve and show how we can calculate it using integrals. So that was really a quick run through on the chapter. There are several formulas that you need to know. You know that net distance, we can do absolute value of v of t dt, and that gets us net distance versus the integral of v of t dt, which gets us displacement. How far are you from where you began? Area between the curves, there, it was like f minus g. We could work in terms of x dx. Otherwise, we can work in terms of y, right minus left. Our bounds, of course, would have to be y values. Volume cross-sectional area, this is easy. We just need to know the cross-sectional area of a typical slab and multiply it by the thickness. When we went into, we talked about circles. Circles ended up being pi over 8 as a coefficient. Right isosceles on a leg was 1/2. Right isosceles on the hypotenuse was 1/4. Equilateral triangle is root 3 over 4. Rectangle is the tricky one. You have to read it carefully, determining, what the ratio is between length and height. And did I miss any? Square is 1. Disk washer shell method. Disk method, we only have one radius of rotation, either dx or dy, and it's pi r squared. If I get into a hole where there is a hole between the axis of rotation or some white space between the axis of rotation and the figure being rotated, then I know I need to use big R and little r squared. That I use x when I'm perpendicular to a horizontal axis of rotation. Shell method is like this. So we need the axis of rotation, or the radius of what's being rotated, and that gets us into a 2 pi r times the height of our shell, which is either f of x or f of y. I'm going to work with f of x here, dx. If my axis of rotation, is my y-axis, then this will turn out, the radius will turn out to be a distance of x. If this axis of rotation shifts, then that's going to affect the radius as well. And I would just do right minus left once again to get the length of that. Length of a curve, what was the formula for that? It was the square root 1 plus f prime of x, quantity squared dx. You could also work in y's. And normal distribution, I will give you the formula for the Gaussian curve on the test. Just know how to use it in your calculator, know what mu represents and standard deviation, and be able to answer any of those questions. But I think that covers it.